Okay, so it's 4 o'clock. Let's get started. It gives me great pleasure to introduce our speaker today, James Osborn. James started out as a PhD student in Durham by chance at the same time as I. Whilst I was messing around with simulations, James was busy getting his hands dirty with instrumentation work, and that paved the way for a promising career. It's been pushing ground-based observations to the limits. After his PhD, he moved to Católica in Chile as a postdoc. I kind of followed him there, but I'm not a stalker, I promise. He then returned back to Durham. There he's currently Associate Professor, as well as UKRI Future Leaders Fellow at the Centre for Advanced Instrumentation. As we'll hear, his work focuses on modelling and eliminating the effect of atmospheric turbulence in optical observations. So whilst his work has touched astronomical sites from Paranal to La Palma, he's not restricted himself solely to ground-based endeavours. He recently turned his focus to the issue of satellite transit that I know we fret a lot about actually in Weave and Foremost. Thanks, Elon, by the way. Whilst also working on the reverse problem of transmitting data to satellites back to Earth through the atmosphere. So it gives me great pleasure today to welcome James as today's speaker on stopping those stars from twinkling. Thanks. Over to you, James.
Thank you very much, David. That's a nice introduction. So, yeah, sorry I couldn't be there with you. I wanted to come down and be there in person, but well, things happen, don't they? I hope to come down one day soon instead and have a good meeting. But yeah, so thank you for the introduction. So first of all, I'm not an astronomer. My interest really is in the Earth's atmosphere, and specifically what happens to light as it travels through the Earth's atmosphere. And obviously, we're all aware of this for optical astronomy, but what I've recently found, and is the subject of my fellowship actually, is that the same techniques and ideas that we use for optical astronomy can indeed be transplanted into other fields like laser communications or satellite tracking, for example. So today what I'll do is I'll put down some of the basic ideas of optical turbulence, which some of you I'm sure will all be aware of, together with some of our capabilities from Durham, things that we've been working on, instrumentations, models, and this sort of thing. And then some mitigation techniques as well, both for adaptive optics, to correct for the phase, but also some scintillation correction techniques, which are perhaps less well known. And then also address or show how they can be used in these art fields. Okay, so to start with, I'm a member of the Centre for Advanced Instrumentation, which is a part of the Department of Physics in Durham University, up in the north there, little circle for those of you that are not aware where Durham is. We've actually got 2 sites. We've got one on the University Science site, which is the top picture there in the centre. That's the building I'm in right now. And then about 20 kilometres away, we've got another site which we mainly use for assembly, integration and testing. We've got lots of optical labs down there, for example, in a place called Sedgefield. On a whole, we're about 70 people in the group in the Centre for Advanced Instrumentation. It breaks down at about 20 students, 15 PGIs, 20 engineers, 15 academics, that sort of level. And we cover everything, mainly optical instrumentation. So we've got things like spectroscopy, biophotonics, fusion diagnostics, all this kind of thing. But the things that I want to talk about, really, which joins together space science, adaptive optics, and free space optics. Okay. So we'll start at the beginning and work through. So I imagine lots of people already know a lot about this already, but effectively atmospheric turbulence is caused by temperature variation, okay, which changes the density and how the refractive index of the air, and there's temperature variations which are driven by some sort of mixing mechanism. And that could be wind shear or it could be convection near the ground, for example. And these refractive index variations distort the light as it travels through. So as the electric field goes through the turbulence, you get a phase component and an amplitude component. And this causes an image to appear blurred and to twinkle. So this is a simulation on the right here in the animation. You've got the wavefront phase on the top panel, and then a simulated image on the bottom panel. And you can see that it breaks up into speckles. There's some sort of chromatic aberration going on there as well. And if we were to look at a star through a large telescope, this is what we would see, right? So if we wanted to look, for example, at an extrasolar planet, then you've got no chance, right? So my work really is about trying to understand this process and trying to mitigate it so we can get more information out. Now, I mentioned before that there's also the phase component and an amplitude component. In astronomy, we generally only talk about this phase component, which causes this sort of image to speckle and to move around and to wander. But actually, if we look at the amplitude component as a function of propagation distance, okay, so if you imagine that the turbulence is a sequence of lenses, as you move away from a lens, then it starts to focus the beam, right? So in the same way, if we've got this large spatial varying focal length, then as we move away from that, we get images start to appear. So actually the animation on the right here shows what happens to the amplitude, the intensity, if you like, as you move away from the turbulence. Okay, so it's going a lot longer than the normal astronomical case. It starts at 0 and goes all the way up to 100,000 kilometers, 100,000 meters, sorry, 100 kilometers. But you can see that the intensity isn't flat. Okay, the intensity breaks up into these speckles. And that would be the pupil plane of your telescope that pick up on these speckles. And that's what, when you integrate that, you get the intensity variation. Okay, so there's another example which is perhaps more tuned to the astronomy case. The animation in the middle here would be the image in the pupil of your telescope. Okay, for a normal atmosphere, so some turbulence at some altitude is propagated down to the ground, and we get these intensity variations. So when we integrate all of the light within the pupil, then we get the image of our telescope actually changes intensity with time. So as we get one of these bright blobs move into the telescope, then the global intensity goes up. When the bright blob leaves the telescope, the intensity goes down. Now, normally in astronomy, you do longish exposures and you average over all this, and it probably doesn't matter. But for example, if you wanted to do time-resolved photometry, perhaps to look at extrasolar planet transit, then this can be a limitation. And as we'll talk about later as well, if you're trying to send data over a laser signal, then each time you reduce that intensity, you get a drop in your signal. That cancels, you get a lower signal-noise ratio and a higher bit error rate. So it limits the bandwidth of the communication. So actually, where in normal situations, scintillation, these amplitude effects aren't necessarily a problem for normal optical astronomy, there are some cases where we do need to consider it. And in other fields, it's critical as well. So I'll talk a lot about that as well. So basically, in the field of optical turbulence, my work basically breaks down to this. Okay. Ideally, if we're building some system, whatever it is, whether it's for astronomy or laser communications, whatever we want to do, we need to know where it's going to go. So we need some sort of survey type tool which enables us to look over the whole world and decide where is the best place to put something. And that comes down to a global forecast, right? So we can use meteorological forecasts, much like we do for the wind or temperature or clouds, and we can use that to extract turbulence. Okay, so this is something which I'll show you in a minute. Once we've got that, then we need to, it's only a forecast, right? So in the same way that rain forecast can be wrong, so can turbulence forecast. So we follow that up with site measurement, okay, using some turbulence monitoring instrumentation. There are lots of ideas here of things that we could do, but you might follow up on a few of those sites, the key sites. Maybe for laser communications, for example, you want a network of sites. So you would need lots of potential sites all around the world, such that you have continuous coverage. And we might want to know what the turbulence is like at all of them. Once we've done that and we've got a good idea of what we think the turbulence structure is like at any place where we're going to build our system, then we need simulation and modeling work, right? And this enables us to design an instrument specific for that location and also performance forecast. So if we need to know that want to build an AO system for an extremely large telescope, for example, then we need to really understand the characteristics of that site in order to help us define that adaptive optics system. And that comes down to the turbulence mitigation, right? When we're actually running on sky, if we know what the turbulence is doing at any one time, then there are certain things with an AO system that we can tune in order to optimize the performance. We might want to change the scheduling such that we do certain observations when the atmosphere happens to be weaker. You know, you could imagine if you want to look for an Earth-sized planet around a sun-like star, maybe you need exactly the right conditions. So if you can really understand that site, and maybe you can even forecast the conditions of that site, you can make sure that you're using the right instrument at the right time. Okay. So this is effectively what I do for every application that we're talking about. Actually, I said at the beginning, I'm not an astronomer, right? And that's true, because in certain respects, a bit flippant, but I don't care what the application is. I don't care if we're talking about astronomy or laser communication, same process that we're doing it all. It's all about getting light through the atmosphere. So adaptive optics in itself, most of you be aware, but for those that aren't, it's conceptually quite a simple idea, right? Some light comes through the atmosphere. We have a deformable mirror, right, which we have to create a shape on, such that when the light bounces off that mirror, it's flat. Okay, so it's taking out those distortions in the shape of the wavefront. After the deformable mirror, we have a beam splitter. Okay, some of it will go to your science instrument, whatever that is, whether it's a spectrograph or an imager or whatever. And then the other beam goes down to the wavefront sensor. And this is the part which measures the residual wavefront that's left over after we've done the deformable mirror, because there's always going to be some residual, through a real-time control system, which tells us what shape to put on the deformable mirror, and then we update the shape of that deformable mirror. This is what we call a closed-loop system. We measure the residuals of the AO system, and then reapply those residuals. And then as the atmosphere evolves, as it changes with time, the shape on that deformable mirror will change as well, such that we always get the best possible correction that we try to target. Here are some examples from a simulation. This is from a SOAPy AO simulation, which is developed in Durham. And if you want to experiment with adaptive optics simulation tools, this is a good one to choose. It's always in Python. It's freely available on Git. You're welcome to go and look at it. So the panels on the left show a diffraction limited point spread function and an azimuthal average on the bottom. So you can see that we have a standard area pattern. This is in a log scale, so you see lots of features there. But if we did no correction at all, we'd have the instantaneous image shown on the next panel along. And this is where we see all that speckling that I showed in my simulation before. But this is now in a log scale, so you see a lot more structure there. Usually in astronomy, we're talking about longer exposures. So all of these speckles, as the atmosphere evolves, they all move around and they boil, right? So over a long exposure, actually we get quite a smooth point spread function, but it's blurred, right? It's much bigger than the diffraction limited one. And that means that we're losing information. We can't extract as much information from the source as we'd like to. The image on the right-hand panel then shows the AO collective point spread function. Okay, and you can see that we're not getting the diffraction limited PSF back. There is some residual. And what tends to happen is you seem to have a diffraction limited core sitting on top of an uncorrected halo, if you like. Because we're correcting some orders of the phase, but not all orders. So whatever your AO system is, there's always going to be residual error. And depending on what your requirements are, you have to tune your AO system to minimize that to get down to those requirements. Okay. Here's an example. This is the first example I can find of an AO system in astronomy from the COMON system in 1990. You've got the uncorrected image on the right. Okay, and you can see it just looks like some blur. You turn on your AO system, and then all of a sudden, yeah, brilliant. Okay, you can see there's actually two stars there. This is what we're trying to achieve. Okay. Now, I mentioned before about the scintillation, about these amplitude effects as well. And at the moment, there isn't really any correction technique for scintillation. Okay. So if you did want to look for an Earth-like planet around a sun-like star, maybe if you're doing that from the ground in looking at transit photometry, you might be limited, in fact, by the Earth's atmosphere, which might limit you to seeing things more Jupiter-sized than Earth-sized. So what we've been really thinking is there something like adaptive optics, right, which corrects the phase of the wavefront? And really what we've done, the best idea that we can come up with is to tomographically probe the Earth's atmosphere. Okay, so we use either stars or laser guide stars even, in order to illuminate the Earth's atmosphere. We then have a wavefront sensor which collects all of the wavefront aberrations in several different directions. And then in our computer, we can tomographically recreate that volume of the turbulence in high frame rate. Okay, and then rather than doing a real-time correction as we do with adaptive optics, what we do is we calculate what the scintillation would be for that atmosphere, and we can then numerically subtract that from the measurement. Okay, so actually it can happen in post-processing as well. And in simulation, okay, this is all in simulation at the moment, without this system in place, you get the panel on the left shows the blue crosses of your measurements, for example. And the black line there is the transit that we're trying to find. So as the planet goes in front of the sky, you get this little drop in intensity, and that's what we want to try to extract. With this tomographic technique in simulation, using a realistic atmosphere, we get the green point. Now, as we all know, right, everything is doomed to success in simulation. So we're currently working on an on-site trial of this technique, okay, but it's not working yet, but we're getting there. So on to atmospheric turbulence then. So most of you will be aware of which is the Freed parameter. But roughly speaking, the Freed parameter, or R0, is the size of a diffraction limited telescope. So if you've got an R0 of 10 centimeters, that would tell you if you had a 10 centimeter telescope, it'd be diffraction limited, right? If your R0 was 20 centimeters, then a 20 centimeter telescope would be diffraction limited. So an R0 of 20 centimeters signifies weaker turbulence or better observing conditions in 10 centimeters, for example. So an important parameter then is your D over R0. A D over R0 of 1 would be diffraction limited, right? A D over R0 of 4 would be sort of the case where you're moving away from diffraction limited, where you're starting to break up into these speckles. And then, for example, D over R0 of 10, you're really atmospheric limited rather than diffraction limited. Now, R0 in the Earth's atmosphere tends to be around about 10 centimeters for a reasonable size. So when we're talking about 8-meter class telescopes, even 1-meter class telescopes, really, we're nowhere near the diffraction limited. So we're always going to be atmospheric limited. Our resolution is limited to that of a 10 centimeter telescope, effectively. Okay, we have a bigger light bucket, so we have more photons, but our resolution is limited. This is the real driver for adaptive optics, is to enable us to really exploit the full potential of the telescope. Another parameter which we often talk about in atmospheric monitor is the isoclimatic angle, which basically tells us the correlation of the turbulence as a function of angle. Okay. Now, in adaptive optics, this is important because if you're correcting for one particular direction, where your guide star is, where your probe is, then as you move away from that, you lose correction. Okay, so here's an example from the VLT in Chile, where we're looking at some cluster of stars, and on axis we get extremely good correction, but off axis it's not so good, right? And the isoclimatic angle will tell us how far off axis we can look with our AO system. Another parameter which we need to think about when we're talking about atmospheric turbulence is the coherence time. Okay, my clever animation, I was trying to be too clever, and it's broken a bit here. But you can see basically as something moves, as the atmosphere moves slowly, then your PSF will evolve slowly. If it's moving quickly, your PSF will evolve quickly. And this is a big problem for your AO system because it's basically the driver for the real-time control system. Now that's easy on a 1-meter telescope, for example, but if you were trying to do this on an extremely large telescope where we have lots and lots of elements in our wavefront sensor, then that's a big computational problem. So we need to be sure that we can drive out the formal mirror at the rates that are required in order to meet our requirements for whatever the science is on Harmony or Mikado or whatever our instrument is. And this is even worse, in fact, for laser communications, where perhaps we want to send a laser beam to a satellite in low Earth orbit. Right, that's moving across the sky at half a degree a second. It's moving very quickly. So that will amplify this effect. Another little animation here is, so we're going back now to what we actually do. So that's the introduction to the parameter space that we want to explore. Now, as I said before, we can use meteorological models, right, which gives us the vertical structure of the Earth's atmosphere in terms of pressure, temperature, wind speed, humidity. We've then devised a model which can turn those meteorological parameters into optical turbulence. And this is the output of that model on a global scale. Okay, so each frame here is a 3-hour step in meteorological forecast. And the color indicates the seeing. This isn't the Freed parameters, this is almost the inverse of the Freed parameters. Astronomers in the audience will know about seeing, I'm sure. Basically, a larger number is worse, more turbulence is stronger turbulence. Okay, but you can see now that turbulence really is a weather system, much like you might see clouds swirling around the world. You can see that now in optical turbulence, and I think that changes the way we think about optical turbulence. Because normally, when you're at an observatory, you're watching your turbulence monitor, and it goes between half an arc second up to 1.5 arc seconds. It might change in a few minutes or something. But really, it's difficult to make that step to thinking, actually, this is a weather system, right? Which means, and when you realize that, you can see that we can forecast it. This gives us hope that we can forecast what the conditions will be like in 10 minutes time, half an hour, 10 days time, essentially. In 10 days time, you're not going to be able to tell you, at this hour the thing will be X, but we will be able to tell you if there is a weather front coming, right? If you have a turbulent front coming through your observatory. And I think that's quite an exciting proposition. The other thing that you see in this diagram, right, is you see some strobing going across the land mass. And that's from the solar heating of the day, of the ground during the day, and then re-emitting, right? So you get convection, rise and turbulence near the ground, and that shows in this model as well. That's all included. There's a lot of information here, which I think is useful for all of these applications. And right now in astronomy, we're getting to the point where we have these models in place, but I don't think they're really utilized yet. We want to be able to say what instrument or what observation program we should be doing at each point in the night, depending on which forecast the turbulence conditions will be. I think that's quite an exciting idea. What we can do, okay, so that's an animation, but we can look at the average turbulence strength. So now I'm changing units again, I know. This is now Cn squared, which is the refractive index structure constant. It doesn't really matter what these units are for all of these things, but in this case, a bigger number is worse, the stronger turbulence, much like in seeing. And we see that there is this day-night variation, not over the ocean, actually, as it happens, but over the land, we get this big difference, and we get a difference in altitude as well. So it's maps like this, and okay, not only the average, but actually when we have that full animation, we can work out higher order statistics as well. What is the variance depending on where we want to be in different seasons and different months potentially. So now, if you want to build a new telescope, we can find new places to do that. If you want to build an optical system for whatever it is you want to do, we can really find the best places in the world to do that for both clouds and for refractive index. Okay. Now, it might be that we already have a telescope, we have the BLT, right? We're not going to move something like that. We're not going to build a new one, but this enables us to really understand the site statistics. In terms of the parameters which I introduced before, then the free parameters of the coherence time and the isoplanartic angle are the big three. So we could do maps of those things as well together and separate it by day and night. So, for example, in night, the free parameters, as we would expect, because the turbulence is weaker during the day. The coherence time has a bigger day-night variation as well. So we know then that is being driven by the ground layer, because that's where the big difference is between day and night. So often with coherence time, we think that that's driven by high altitude turbulence, right? Because that's where the fast stuff is. But actually the strong stuff near the ground also has a significant impact on coherence time. And then isoplanartic angle, again, generally is driven by the high altitude things. And you can see the sort of the striping going across sort of the mid latitudes on the panels on the right. And that's driven by the high altitude, okay, where we get these jet streams, these belts of high altitude turbulence. But we also have, over the land mass, we have variations between day and night as well. So there's significant input from the ground layer side as well. So all this just helps us to understand what's going on. And when it comes to atmospheric monitoring, now we'll move on to actually measuring. So, forecast is what it is, but if, weather forecast would be nothing if we didn't have the data of simulation, if we didn't have the measurement devices as well in order to do the validation and the optimization. So in terms of atmospheric turbulence monitoring, really there's several reasons, which I've already mentioned a couple of times: site selection, instrument design, performance verification and optimization. Also post-processing, right? If you've got a site monitor at your observatory and you know what the atmosphere is doing at the same time as your data, then you can try and regenerate your point spread function due to the atmosphere and deconvolve that, right? Try and extract more information from the point spread function. And then scheduling and operational decisions as well, obviously. So now I'll just tell you a little bit about how these monitors work, because you might not know this, right? You might see that some site that maybe you go to the very large telescope and you see that the seeing is half an arc second. Well, how do we get that number? Okay. Well, the gold standard, what we want to do is some sort of tomographic technique. I already introduced this idea a little bit with the scintillation, but effectively, if we look at two stars through the Earth's atmosphere, if all the turbulence is at the ground, the pupil of that telescope, then it doesn't matter where in the sky we're looking, the aberration that we measure will be the same in both directions. It doesn't matter whether we're measuring in phase or measuring in intensity, it's the same in all directions because all that turbulence is at the ground. If that turbulence is slightly higher up, then actually the aberration that you measure in different directions is shifted with respect to one another. So when we calculate the correlation of the aberration of one with respect to the other, we get a shift of that correlation given by h times theta, right? The height of the turbulence multiplied by the direction, by the angle between the two directions. Okay, and then as that turbulence moves higher again, we get a higher displacement or a larger offset of those two aberrations. And when we calculate the cross correlation, we get an offset, standard data signal processing kind of thing. And this offset in the correlation tells us the altitude of the turbulence, and the magnitude of the correlation tells us the strength of the turbulence. So that's how all of these techniques work, really. If you ever see a turbulence profile, this is what it's doing. Okay. So again, in simulation, because it's easy to see, if we've got a low turbulence, a low layer turbulence, a low altitude turbulent layer, then it'll appear at the center of this cross correlation function. So now, unlike data signal analysis, which maybe you've come across before, this is now a 2D plot of correlation because we're working in multiple dimensions here. It's not just a 1D data signal. And if the turbulence is at some altitude, then actually we get this new spot in the turbulence in the correlation map, which is offset from the center. Okay. Now on the left we show simulation, and on the right is exactly the same thing, but with real data. This is from one of our instruments at Paranal, actually. And again, you can see that the ground is this thing in the middle. And as we go up on this axis, we're going up in altitude through the atmosphere. And in this case, we can see just by eye that we've got 1, 2, 3, 4, 5, 6, 7, maybe 8 turbulent layers going up in the atmosphere. Okay, so already we can see, without doing any data analysis really, that the Earth's atmosphere, the turbulence, isn't just some continuous volume, but it's got very discrete layers as part of it. And we can do this both in phase, so we can use a wavefront sensor like you would in an adaptive optics system to get this to measure aberration, or we can do it in scintillation, right, measuring those intensity variations that I showed you before. When we do it in phase, it's called a slowdar. When we do it in scintillation, it's called SIDAR. So slope detection and ranging, or scintillation detection and ranging. Here's an example of a stereo SIDAR system that I built at Paranal. There's a photo on the right. This is the auxiliary telescope 3, which is a 1.8 meter telescope. We've got the UT, the unit telescope, the 8 meter telescope behind there. And from this AT, this is the data we get, right? So here is the profile of the turbulence as a function of time on the x-axis, altitude on the y-axis, and then the color indicates the turbulence strength. I've actually cut off the color bar here, which is a bit silly, but this is actually in CN squared units. So it's in the logarithm, so you can see there's always strong turbulence near the ground. At Paranal, the ground area is quite thin compared to other sites. But also we get these very discrete turbulent layers, which is what we saw before, right? So it's not just some big blob of turbulence, but there's these layers, and they change in altitude, they change in strength. It's all very variable, it's all very dynamic. And which means that when we want to build an AO system, we're not just trying to correct for some big volume of turbulence, but maybe if we want a wide field system, we can correct for each layer independently, for example. By understanding this, there's a lot more we can do. Another thing that we can get from this area SIDAR, so this is the cross correlation that I showed you before. It's just another example where each of these blobs indicate a turbulent layer. But this is the correlation, right, of two different directions with an angle between them. But if I put a temporal offset between direction A and direction B, and I step through them, then I get something more interesting, right? So now each of these layers, each of these blobs in this correlation function indicates a turbulent layer, but because I'm adding a time delay, I've got time and space, which gives me a velocity, right? So now each of these blobs are moving in this cross correlation map, and the velocity by which they move tells me the velocity of the turbulent layer. So not only do we know the altitude and the strength, but we also know the velocity of the turbulence. And actually, this is something which we're currently struggling with, because there's more information here that we can see by eye than we can get a computer to pick out very easily. So we can see before, there are 5, 6, up to 8 obvious layers that we can pick out. But when we look at this movie, you can see that actually there's a lot more going on there. That when we see them move, the human brain is really good at picking out this motion. And you can see there's perhaps 20 or 30 different blobs there, all moving with different velocities. And we can also see that they tend to break up into some sort of velocity dispersion into an arc. Right? What does that mean? That's what it means that there must be some velocity dispersion in the atmosphere, some sort of wind shear and direction, as well as velocity, as well as speed. Right? So there's lots of information here that we're still trying to extract. Another thing that we can do is we can measure the atmospheric turbulence day and night. So this is a new capability that we're building on now. It's just hot off the press this year. We've got a paper in preparation at the moment, because usually we measure our turbulence either at nighttime or at daytime with a different set of instruments for both, depending on what we want to do. And actually, the instrumentation for measuring atmospheric turbulence during the daytime is difficult, right? It tends to use the intensity-based method, and actually in strong turbulence, that fails, right? That doesn't work so well. So we want to use a phase-based method, and what we're using is an in-gas camera, right? We use a shortwave infrared camera, and we look at stars during the daytime, and at nighttime we look at exactly the same instrument that can work continuously for 24 hours. This is quite a significant step forward. And the plots here are the freed parameter R0 on the top panel. And you can see that we've got measuring an R0 between, I don't know, 10 and 15 centimeters or something during the night. This is in La Palma, by the way. We then have a bit of a gap at about 6 a.m. when the wind speed got too high and we had to close, which is unfortunate, because I was really pushing for a continuous 24-hour sequence, but we've got this break in it, which is frustrating for me. But then during the day, we can see that the turbulence gets a lot stronger, as we expect, because we get that solar heating during the day. And the turbulence, even on La Palma, which is one of the best observing sites in the world, goes down to perhaps 3 to 5 centimeters, and then back up to 10 to 15 again at night. And I've also got the isostatic angle on the bottom panel as well, which is another parameter that we can extract. Now, the great thing about this monitor, which is it's a new development, as I said before, not only does it work day and night, but because we're doing it in phase-based rather than intensity-based, which the daytime one tends to be, it means we can do it in strong turbulence conditions as well. So generally, all turbulence monitoring is done in nice and calm astronomical observatories. But as I mentioned before, we're starting to get more interested in other applications as well. So we have a system working in Durham, right, which certainly isn't a nice, calm astronomical observatory. So in this case, this is in both of these now are in local time. So we've got freed parameter on the top 2 plots, just 2 different nights. They're starting at 2 in the afternoon and going to 8 at night, and this was done in the winter, so sunset was about 5 p.m. So we're seeing now the transition between day and night. And actually in Durham, there's not so much difference. And you could make the argument potentially that Durham might be a better observing site during the daytime than the Palma, perhaps. Not for clouds, obviously, but for turbulence. And that's because we don't have that really strong solar heating. Now, at nighttime, the turbulence is much stronger in Durham than in Palma, because we don't get those calm conditions coming through. But it's interesting now that we have turbulence monitors that this is a portable system we can take anywhere in the world. So we can start doing this thing where if we want a network of laser communications, for example, where should we put them? Well, we can work out where they need to be based on the forecast and follow up anywhere in the world based on this monitor. As an example, here's something we did in London. This is on the roof of a bank in the city of London. And again, we've got R0 on the top panel there, the freed parameter, which is about 4 centimeters, between 3 and 4 centimeters at night time in London. So if we want to do something, for example, banks are really pushing for low latency quantum key distribution, because that means they can exchange quantum keys effectively with other banks in Frankfurt or New York or wherever they want to go to. That needs to be near the source, right? So we need to have laser communications in urban environments near our data centers. So we need, and at the moment, we've got no idea what the turbulence conditions are at these sites until now, because this is the direction we're pushing. Another technique, slow DAR, slope detection erosion. I mentioned this before. I just want to flag this up as something we do. So we have a half-meter telescope at Paranal, which is the picture on the left, and another half-meter telescope, in fact, on La Palma. This is on the roof of the William Herschel telescope, which is the one in the background there. And we have a slow DAR system, so we get the vertical profile of the atmospheric turbulence there as well. And actually, these systems only profile the ground layer, so the turbulence very close to the ground. It's Tim Bosserly that really pushes this. Some of you may know Tim. And we see that even when we're looking very close to the ground, that the turbulence is really concentrated in the first few tens of meters. And that's it, right? At nighttime at least. We don't get these plumes up to hundreds of meters. It's really thin, strong turbulence near the ground. And it's probably driven by wind loading round obstacles, around the WHT building, for example. As we go around the corner, then that causes some wake in the air, which causes the turbulence as we're mixing air at different temperatures. We can also do it from adaptive optics telemetry. Okay, so here is an image of GEMS, which is something I did when I was down in Chile, on the Gemini South Observatory. And the plot on the left now is exactly the same as the one I showed you from the SIDAR. We've got time along the x-axis and then altitude on the y, and the color indicates the turbulent strength. And you can see, again, we have this strong turbulent layer at the ground, and something around sort of 12 kilometers, which is the jet stream down over Chile. And you can pick that out from your aerotelemetry. But the point I want to make here, right, is this is using data that we would get from our adaptive optics system, but it's not an instrument that's specifically designed to do turbulence monitoring. So if I go back to this slide, okay, so this plot here is exactly the same thing, so same idea anyway, but on a much smaller telescope. So we've got an 8-meter telescope compared to a 1.8 meter telescope, a 2-meter telescope. But the information we get when we have an instrument that's specifically designed to do the task is so much more than something that we would get by just reprocessing adaptive optics telemetry data. Okay. As a bit of an overview of the facilities we have, so we work a lot on La Palma. On La Palma, we've got a half-meter telescope, which is a robotic telescope on the roof of the William Herschel telescope, which is here. We do time-resolved photometry on that telescope as well. We also have a slow DAR system and a SIDAR system on there. We've got an adaptive optics facility on the WHT called Canary, which was a demonstrator. It's actually probably the only experimental adaptive optics system that's available. So if people have got ideas to develop new concepts for adaptive optics, that's something we can do with Canary, which you couldn't do with the facility system on the VLT, for example. We've also got a laser guide star facility. This is a laser guide star which is in a shipping crate, effectively. It's a modified shipping crate, so the lid can roll off and then the laser comes out like some sort of James Bond villain. And that's a facility that we can use with our AO facility. We also do other experiments like looking at variations and all this kind of thing. And actually, this is designed such that the laser guide star is 40 meters away from the WHT. And that mirrors the geometry of the extremely large telescope. So we did lots of experiments here to try and work out what a subsection of an ELT might look like using a laser guide star, which is so far off axis that the ELT is so big. We also use the Isaac Newton telescope, the 2.5-meter telescope, where we do a lot of our development work. So we have a stereo side arm there, which is one of these scintillation detection and ranging instruments I showed you before. A clone of the one at Paranal, really, the 1.81. But that's sort of our gold standard, right? And when we do all of this turbulence, developing new turbulence monitors, we always take it to the INT and we do comparisons, we do cross comparisons between the SIDAR and whatever new instrument we're building. And then the JKT, we did a lot of development in the early days on the JKT, which is one telescope up here, but not so much anymore. It's harder to get access to that now. We also have a lot of facility at the ESO Paranal, at the site of a very large telescope. These are the 4-unit telescopes, a very large telescope with their AO facility. And this is the stereo SIDAR, which is the data I showed you before, was from this telescope here. And actually, we were there when they were doing the commissioning of the laser guide stars in order to optimize the tomography that they do with the AO system itself. Okay, so we're involved with the AO facility, the AOS of the UT. We also have our surface layer flow dart, which I showed you the slide of Tim Butterley, that's down here. And the mass dim is up here. Okay, so there's lots of things going on both at Paranal and La Palma. Now I want to talk a little bit about application. Okay, so astronomy is one application. And in astronomy, we've got a ground-based optical telescope, looking at some object, whether it's a galaxy, an exoplanet or something. But actually, when we're looking at free space optical communications, we've got a very similar problem. So in this case, we have a constellation, right, of satellites, and they're all communicating with each other, generally radio, and they may talk to a geo bus as well, which is then has visibility over a larger area, and that has a feeder link, right? So that's how you get your audio information into your constellation, generally goes to and from a feeder link. But the radio has real issues that it's broadcast, right, which generally means it's insecure. It's low bandwidth, which is quite a long wavelength, and with congested frequencies. At the moment, we're pretty much at the limit of our capabilities in the radio. So there's a big push now towards optical. So optical's low power and weight, it's low size, it's very high bandwidth, and it's secure because it's directional. And it enables things like free space quantum key distribution, which I mentioned before. So two parties can exchange quantum keys in a trusted way over long distances. So the idea here is that to communicate with either GEO or LEO in the optical is essentially exactly the same thing as we're trying to do looking at galaxies. It's all the same technologies, all the same techniques. And this is really the subject of my Future Leaders Fellowship, is taking these ideas from astronomy and moving them in other directions. And we could even go further, right? We can even talk about space exploration. We can talk about planetary exploration, lunar bases, for example, and even horizontal as well. It's all the same technology. And we can even go to another direction. We could talk about space surveillance and tracking. So this is where we want to look at things in space. At the moment, believe it or not, right, we don't actually know where things are when we put them up there. Okay, so you put a satellite in LEO, you know roughly where it is. You get some telemetry back, but we don't know exactly where it is. We don't have the technology to know where everything is at the moment. There's about 4,000 active satellites in orbit at the moment. Now that goes up to maybe anywhere between 30 to 100,000 pieces of stuff, right, bigger than 1 centimeter, depending on what model you use. And I say depending on what model you use because we can't see it, okay? We don't have the technology to see the small pieces of things moving around the world. We don't even have the technology to continuously monitor all the big things. So let's say you monitor the position of your satellite every other day, for example. Is that good enough to know to project where it will be and project collisions? So what we really need to do is to build on optical techniques. We could do this in the radio, obviously, but they're massive, expensive pieces of kit, and there's maybe 4 or 5 around the world. In the optical, which is small, lightweight, it's easy, it's replicable. We can put it anywhere around the world. We can have hundreds of these units, which can then continuously monitor the space environment. And that's to make sure we know where everything is, so we can stop things crashing into each other. But also for monitoring. At the moment, there's no real regulation in space. There's some policies that people have to adhere to. But in order for regulation to work, there has to be some sort of policing to work. And for policing, you need monitoring, which is where we're really pushing towards optical technologies, adaptive optics, for example, or even just wide field surveying, which is something we do a lot of in astronomy, in order to monitor the positions. And it also ties into things like laser ranging, which is sort of a really precise way of knowing exactly where something is, potentially even directed energy, which could be used to power satellites or potentially to deorbit satellites or debris, which is something which a lot of people some people are working on at the moment. So this is sort of my workspace, right? This is all the things that I'm interested in currently, but there's one thing missing from this map, right? And that's the Earth's atmosphere. All of this, in order for it to work, you have to get light through the Earth's atmosphere and you have to have the information. It's all about retaining that information that passes through optical turbulence and your electric field, gets these distortions, which have a phase and amplitude effect. Okay, so if we go on to free space optical communications, basically, in this case, you have a laser for your downlink. A laser comes from the satellite to your ground station in the same way as you might look at a star. And that's fine. You can use adapter optics if you want to improve that. But the real problem is to get data into space. So if we want to do an uplink, right, a feeder link, for example, which is what we call these big pipes, big bandwidth pipes, to get all the data into space, then we need to point to where the satellite will be because the satellite's moving, right? So your uplink needs to not point where the downlink comes from, but a small angle away, such that when the light gets to the satellite, that's where the satellite will be. But the problem is that that link is not reciprocal. So we can't really use the downlink beacon to correct our uplink. So what we do is we borrow another technology from astronomy. We use laser guide stars. Okay, so here is a photo of our laser guide star facility at La Palma, which I showed you before. This is actually me here standing next to it for scale. This thing's about 2 meters long. It's a refractor, so we don't have a central obscuration. And this is 20 watt laser beam at 589. So this photo hasn't been photoshopped or adjusted in any way. Like standing next to the laser, it looks solid, right? It's actually an incredible piece of kit. And actually, our newest lasers are up to 70 watts now, so it's considerably high intensity than this. And we're currently working on a project with ESA in order to build a technology demonstrator exactly for this, to build a blueprint design that can be used for a global network, right, in order to get data into space. Tying into our modeling side, okay, so we have lots of simulation platforms and modeling platforms which are all geared towards modeling the propagation of light through turbulence. So here's some examples from that, just to show you, give you a bit of an understanding of what light looks like after it's going uplink through, as we're getting data upwards. The top panel here is uncorrected, okay? So this is 20 meters, well, 40 meters by 40 meters, in fact, this panel. And if we don't have any sort of turbulence mitigation, our satellite, the receiver on our satellite is about 20 centimeters in size. So that'd be 1 pixel as middle here. So if you imagine that if you're collecting the light in the central pixel here, most of the time, you're not getting any light at all. If you're lucky, you might get one of these speckles come through and you get a lot of data. But most of the time, you don't get any. This is what's called a fade, right? And we have quite a high bit error rate. So that doesn't work. We have to have some sort of turbulence mitigation. So the easy thing to do is just use tip tilt correction, right? Just literally correct the pointing of that. And that's this panel here on sort of the middle row on the left. And it's better, right? You get light more of the time, but you're still breaking into the speckles, which means you get these deep fades to the data. Now, if we use the downlink from the satellite as our beacon for the uplink, as I said before, the path isn't reciprocal. So we have a large residual error, but it's still better than no correction at all. So now we get light most of the time, but it's still not great. If we use a laser guide star, which is the bottom panel on the left, you see we get a really nice point spread function, a really good correction, but that is still wandering around, okay? So we're still getting the case where, although most of the time we get a lot of light, sometimes we still don't get any. So there's still limitations to this technique. And actually, there's a big push both in astronomy and in laser communications to try and extract tip tilt information from the laser guide star, which would then fix all of this. The reason you can't currently do that is because the laser guide star goes up through the turbulence and comes back down through the turbulence as well. So you have an uplink and a downlink contribution to the tip tilt, and you can't disentangle that. If you're perfect correction, it looks like this, right? So this is what we're trying to do, and at the moment we've got this. Okay, so this is the current state. Another thing we might want to do is satellite laser ranging. So this is where we're finding the distance, the Z to the satellite based on bouncing lasers off it. And we're working with a company called LumiSpace to do this. LumiSpace is the first commercial satellite laser ranging company. And they're really interested in pushing the technology. So we're working with them to develop laser guide star adaptive optics, both uncorrected, again, modeling uncorrected and corrected PSFs in space. But in this case, we're not trying to transfer data. We're trying to get reflection effectively. And if we look at the plot on the top right, hopefully you can see it from where you are, but the blue curve is uncorrected, and we've got return photons per pulse here. And then the orange curve is with laser guide star out. So with laser guide star out, we get significantly more, this is a log scale as well, photons per pulse, which means we'll be able to see smaller objects. So we'll get down to that sort of 1 centimeter scale object, which is what we need to see in order to really understand the space environment. And it means we can do it in the daytime as well, because we have a better signal noise ratio, which means we have custody, we have complete custody, is the terminology that people use. We get to see these objects all the time. If you want to look at something at geo, you want to be able to see it during the day and at night. Another thing that we have significant experience with in astronomy is actually extracting information in low signal to noise ratios. And that's exactly the problem we have in satellite surveillance and tracking. So say satellite arranging is one thing, but imaging is another thing that we want to do, right? We want to collect the reflected photons from GEO or LEO and try and either look at the light curve of that to find some information about it, even just see if something is there or not is step one. And then we can see if we can resolve it or get the light curve, as I say. And so we work with the astronomers here in Durham, and there's obviously space for other people to get involved as well. If people sort of recognize this sort of data and think that they have some sort of ideas, techniques, data analysis pipelines that could be used, this is wide open at the moment. It's a good place to be working because the field is so young. And another example of this, for example, is in wide field imaging. So if we make a full sky camera, for example, which is something we often do in astronomy, then as well as seeing the stars, but we also see the streaks of the satellites. Now, depending on our system, will give us the signal to noise ratio, which tells us how big these satellites need to be or in what orbits they need to be. But basically, on some fairly back of the envelope calculations, we can work out which satellites are observable, right, and which aren't. So in this case, based on the system that we're building in Durham, we should be able to detect a lot of satellites. You're talking, hundreds of satellites a night we'll be able to detect with a wide field camera, specifically the brighter ones. Now, this is important for the reasons that I told you before about monitoring the positions of things to stop them bumping into each other, but it also comes back to astronomy, because if we've got a wide field camera which can pick out the satellites and plot their trajectories, if we know our telescope pointing, it means we have an early warning system, right? We'll be able to know that a satellite is going to cross our field of view in a second's time, right? So you don't get much warning. These things move at half a degree a second, right? So it's 8 minutes to cross the sky. So most you're going to have a few minutes warning that you've got a satellite coming. And if you know that, though, you could conceive of an automatic shuttering process. Okay, avoiding might be difficult, but you could certainly shutter. And if you have that information, maybe that gives you some way of post-processing the data as well, because it'll tell you that you probably do have artifacts in your data at this timestamp. Okay, because remember that the satellite crossing time of your field of view will be a second at most. But if this is ruining a 10-minute observation because you've got one satellite crossing, then it's certainly worth at least exploring this idea of shuttering the focal plane, right? Tying into this is, here's another slide just showing an example of something which I think we've all seen and we're all aware of. But another thing that we're able to do is if we collect this information, then we can quantify it. And that's I'm pushing this from the direction of bespoke instrumentation for satellite tracking. But actually, if you've got instrumentation where you're finding satellite tracks in your data and you can quantify that, then we need that data, because that enables us to inform policy and policing and decision making. There's a lot of people talking about it, there's a lot of people just shouting, and to be honest, that's no good to anyone. What we need is really quantified evidence, and then we can start building a case, either for or against, right? It might be that actually most of the time, apart from a very small package, maybe it doesn't matter, maybe we can think of mitigation techniques, I don't know. But it's all about quantifying this information. Another thing we can do is actually predicting satellite positions isn't awful. It's not great because we don't know exactly where satellites are, as I say before, but we can generally project where they will be. So there's already tools available. So last year I wrote a tool called AstroSat, which you're welcome to go and use, go and download it and go and play with it. And that will tell you if you've got an observation that you're planning on making in the next few days, you can put in your field of view and your pointing in the time, and it will project which satellites are likely to coincide with that field and how bright they're going to be. Okay, that already exists. So that gives you that avoiding possibility. So in conclusion then, there's a lot going on. Basically, we do everything in terms of light propagation through atmospheric turbulence, so it's forecasting, measurement, modeling, mitigation, all tied towards finding the best sites for the instrument design, performance, estimation, validation, and even optimization, statistics, all this kind of thing for many, many different applications, because I don't see this as technology just for astronomy. It's all about getting that amazing knowledge that we've been working on for tens of years in astronomy into these really young and exciting fields. Okay, so if you want to get involved, do let me know, by the way. There's lots to do. Thank you for listening. I'm happy to take your questions.
Fantastic. Thank you very much, James. Let me just switch this one on as well. Okay, so were there any questions from the audience or from Zoom? If you're on Zoom, can you type it in and I'll read them out. Richard.
Yeah, I mean, you showed some very interesting plots of, I guess, the whole world, but many of our telescopes are on tops of mountains. So do you have the spatial resolution in those maps to tell you, let's think Hawaii, Mauna Kea out there. I assume there's some pixel on those maps, right? Are they resolved?
Yeah, I think so. You're talking about the forecast, right? So the forecast data has a resolution of about 10 kilometers square, right? Which obviously doesn't really resolve the top of Mauna Kea or La Palma. Having said that, there's still things you can do, right? Because if you, in the same way that a meteorologist can take that information and interpret it in some way, you can do that, and that has to be done for La Palma. Paranal is actually a really easy case. It's on a ridge line, right? But the mountains aren't that big, so it works amazingly well for Paranal. But places like La Palma are an issue for astronomy cases. Yes, that is certainly true. Yeah.
So I guess the corollary is, are we using the best sites in the world? Are the sites that we're currently investing in the right ones?
Well, that is a very good question. And I guess we don't have the answer to that yet. We still need to do an analysis of that, right, to find out where we should be. I suspect they probably are, you know. Maybe there are some other untapped places where there could be amazing sites as well, in addition to the current positions, and that's what we're actively looking for. Yeah, there's a lot of, we get a lot of work with people, for example, from Thailand, in South Korea, India, Greece, people looking for great sites at their location, in their countries. That's what most of our requests are for.
I mean, it's an iconic picture, I think, ESO, where they showed this guy with a donkey who was obviously out camping to find the best site for farming.
That was Lucia, yeah, I think, yeah.
Exactly. I know. I'm afraid that I missed that golden era of exploration. I wish I could have been part of something like that. But yeah, you know, the forecast is only that. It's a forecast because it's a great indication. I've done comparisons, for example, in Paranal and Mauna Kea in Hawaii, actually. And the forecasts, even on Hawaii, work surprisingly well. I was surprised how well they work. Maybe I can show you. Oh, well, okay, so I've got some reserve slides, obviously. So typically, the mesoscale simulations are these small-scale nested simulations, which tend to be a bit of a buzz at the moment. They go down to maybe 100-meter resolution. So that's the panel on the middle here, is time against altitude for the state-of-the-art small-scale simulation. You're never going to do that on a global scale, right? And then the plot on the left is my equivalent at the same timestamp. So yes, it's not perfect. The structure in the mesoscale model, which we don't see in the general circulation model, the global model. But actually, the big structure, the big things, those big weather features that I was talking about, you can see that. And then another thing the comparison between R0, for example, the breach parameter is the top left. For the mass dim, which is a measurement campaign at Paranal, and then the model, So there's more spread to the model, but actually on average, it's pretty good. This is the kind of thing we get. It's not perfect, but it's a good indication.
Thanks.
Okay, another question at the back.
Almost all of the models that you've been working on, the simulations, have been using what I call long exposure integrating detectors. Have you thought about what can be achieved by using much faster resolution, getting down to tens or hundreds of hertz per frame rate? Given that we now have large area CMOS devices with very close to 1 electron RMS readout noise, and a readout time that can be done in a millisecond or two, maybe we should be looking at that technology as well.
David, maybe you can relay that question. I couldn't quite catch that.
Yeah, so I mean, I guess is it almost like a lucky imaging approach?
Well, just taking pictures quickly and then doing something with them before you all add them up.
Okay, so essentially much shorter exposure times using different detector technology.
To extract turbulence parameters?
Well, you're adding them all before you actually do any analysis on them.
So, well, all of our turbulence monitoring is all based on very short exposure times because you have to freeze the atmosphere. Right? When it comes to something like astronomy, right, then yeah, there's obviously techniques like lucky imaging, for example. You can do nice detectors which are very low noise, and you can add together images. I don't think I've really heard your question though.
Am I allowed to ask? Could I ask a couple of questions actually? Just using my prerogative. So, is your job easier if you go to the infrared? I mean, if we were looking to say directly image protoplanetary disks, for example, I'm guessing it's an easier job. So, can you apply essentially the same techniques there, or is the turbulent modelling just entirely different beast at those wavelengths?
No, you can. You absolutely can, and that would certainly make life easier. And we have now moved to the shortwave infrared. The big question is detectors, right? Silicon detectors in the visible are cheap, they're easy, we understand them, they're great, right? We can have a great model of a silicon detector. As soon as you move to the infrared, that gets a lot harder. Detectors get more expensive. We have to cool them, which makes them harder to put on small portable telescopes. The shortwave infrared has now been opened up thanks to the development in in-gas detectors, right? So that's what we're moving to now, and we can understand that, and we've got a lot more going on. But yeah, ideally, the further red we go, the better. And that means that we go in daytime as well, because the sky is obviously peaks in the blue, and then we get this a strong wavelength dependence on the radio scattering. The further red we go, the more we can do in the daytime.
Okay. And then the final thing for me was this really interesting aspect of the satellite communication in the optical regime. I mean, I guess there's a trade-off here between when you're comparing it to radio, sort of this focused beaming with very high bandwidth where maybe you miss some of the signal versus, so the amount of data you can transmit versus obviously this broad brush radio transmission where you are really painting the target. So, I mean, is it profitable in the sense that even if you are quite low signal to noise, you're losing a lot of that signal, you still get a lot of you get a lot of data or more data than you would through radio?
Yeah, you definitely still beat radio. And the big advantage really is that optical is small and portable and low power. So you can put these things anywhere you want. You know, if you're the military interested, because they can go out into the desert and they can just have a high bandwidth link to back space. Or you could imagine Earth observation getting all that data back. Earth observation, well, most scientific missions are in fact data limited. So getting the high bandwidth is really important. At the moment, we're not as good as it could be. There's still room to improve it more. As you rightly point out, we still get this loss of signal, right, which you don't get in radio, but it's still better than radio.
Okay, so that's an interesting trade-off. Any other questions from the audience? I will note that on that forecast map, New Zealand looked pretty good actually. So
I do like this this little animation. I'm going to write that to you. Yes, yeah, maybe. New Zealand could be good.
There we go. It could be our maybe an Institute of Astronomy jolly to New Zealand and build a telescope. Wonderful. Well, let's thank James once more for his time.
You're welcome. I hope I come down and visit sometime.
Yes, that would be lovely. Wonderful. Thank you very much, everyone. Obviously, there's wine outside, so feel free to take that and enjoy outside in the what remains of the sun. Thank you.
Bye-bye.
Thanks, James. That was awesome.
Oh, you're welcome.